All right, students, let me try another example that was on that list. I think this is the fourth one, number 36 here. It says, calculate the increase of entropy in the universe when you add 20 grams of 5-degree cream to 200 grams of 60-degree coffee. Now it goes to the next page, so that's where I printed this. Assume that the specific heat of the cream and the coffee are both, okay, basically water. You can use the result also of problem 31. All right, well, I don't think we need to necessarily do 31 here, but let me kind of draw a picture here. So I have one piece of material. This is the coffee creamer, and I'm going to add it to a bunch of coffee. Okay, now the coffee was at what? Coffee was at 60 degrees Celsius, and this was at 5 degrees Fahrenheit. And so the first part of this is just to realize that the cream is going to warm up and the coffee is going to cool down, and there's going to reach some final equilibrium temperature. So this takes us back to kind of the specific heat and the thinking before we got to this chapter. So let me just, do this Q1 plus Q2 equals 0, because the cream is going to get energy. So there's a positive number, which I will calculate as MC delta T. And the coffee is going to lose some energy. And so there's an MC delta T for the loss of the coffee. Okay. Now, this will get us to the final temperature. And so taking the cream, which was, 20 grams. So here is 20 grams. And a specific heat of 4.20 joules per gram for each degree Celsius it changes. And then there'll be some final temperature minus an initial of 5. So that's a positive number, and that's why I was saying the energy will go into the cream. And then this one, let's see, we've got the coffee here. Let me just confirm 200 grams, yeah. And we'll do the same specific heat, although as you can see, just the fact that it's the same will cancel off, so I don't really need to do any arithmetic here, because if I factor out the same specific heat and then divide by 0, that goes away. And then maybe another thing to do is to divide everything by 20. That gets rid of the 20 here, and then makes my math a little bit easier. So final temperature minus 5 is left with that term. And 200 divided by 20 is just a factor of 10. So I get final temperature minus 60 equals 0. Now I can kind of do the distributive property. And on both of these, although this doesn't really involve much of a distributive property, given that it's, basically got a 1 out in front. But this is 10 times the final and then minus the 600 equals 0. And so putting the 1 and the 10 together, and then the 600 and the 5 giving me a negative 605, and move it to the other side is now a positive 605. And so now I can get the first part, which I haven't touched the entropy yet, but I need to know how much their temperature has changed. And so 605 divided by 11 is 55 degrees. Okay, so the change has been more for the cream, of course, than the coffee. So the coffee's cooled down a little bit, but not much. And then that will be a change of entropy. And that's where this begins. So if I do the change in entropy of something that warms up or cools down, as you'll see here. Let me not specify whether this is the cream or the coffee, but let me just say it is the change of a bunch of small entropy changes, which if the temperature is changing then unlike the last example one, we can't really just pull this t out. We've got to leave it as part of the system here. But that's actually very doable because we can use the specific heat in its microscopic form instead of its algebraic form. But here's our calculus form. It's mc dt. And then, of course, if you look at this as being either the cream warming up or the coffee cooling down, the m and the c remain constant, and you just have an integral of t dt, which is saying then that the formula for the change of entropy for something like this, not all cases, but for a case like this, would be this calculation. And so I can apply this to both the cream and the coffee and add the two together and get the total change of the universe, as they ask here. So I'll do that. So let me do the change of entropy of the cream. And so the mass of the cream is that 20 grams. The specific heat is the 4.20 joules per gram for each. And I'm going to put Kelvin. It's technically the change of either Celsius or Kelvin. And so even though the author gave us as a change of Celsius, it's a change, so I can interplay the degree Celsius with the degree Kelvin. I don't need to multiply by some, 200 or add a 273. That's not what that means. That means a single degree, a single change in degree. So whether a change in degree Celsius, so in other words, a delta degree Celsius and a delta Kelvin are the same. So I'll just replace the delta degree Celsius with delta Kelvin. Now, I say that because here's where I do need to be careful. The temperature on a Celsius scale is, of course, numerically not the same as a Celsius scale. So we've got to come back and look at our equation. Is our equation talking about a delta or a Kelvin? And you heard me say this, but it's probably worth saying it again. All of our formulas really are on the Kelvin scale, but a lot of our formulas just need a change and therefore won't matter whether it's Celsius or Kelvin. And that could be argued what I did up here, that right here, since I had a delta T, it didn't matter whether I did it in Celsius or on Kelvin, and I decided to do it on Celsius. But now as I get to the meat of this problem, and I have a little formula that's asking for the entropy, I realize that what I need is the temperature on the absolute scale, on the Kelvin scale. And so I need then to put in the final temperature in Kelvin. And so if I take the 273 and add the final temperature of 55, let's see, I get an 8 and the 12 carry 1. And so that's a 328. So the final temperature is 328, and the initial is, 5 degrees. So this would be 278 for I should say 5 degrees Celsius, so it's 278 on the Kelvin scale, and so Kelvin over Kelvin. Of course, the units cancel off. And if I made a mistake with Celsius, they would cancel off, and I would be thinking I'm doing okay, but I really wouldn't be, because the numbers are different. Okay, now, of course, not a surprise that the units come out the appropriate units for entropy. Joule per Kelvin. And it's actually a change, so sometimes we'll put degrees Celsius here, which I guess goes back to we could have left it as degrees Celsius. What else? Oh, notice it's a positive number, which makes sense. The cream is warming up. It's getting into a more random state. And, of course, is cooling down the coffee, so we'll see that the change of entropy of the coffee is negative. It's less of an less random motion because it has less velocity, so it's more organized, so the entropy goes down. So 20 times 4.2 times the natural log of 328 over 278. And it looks like then it's at about 13.89 is the increase of entropy of the cream. And so following that same logic for coffee, where I now have a much larger mass, same specific heat, although they don't cancel off, so I guess that doesn't really matter if it's the same or not. But I do have the natural log, and then here the final temperature, again, in Kelvin is 328. The initial, let's see, was 273 plus the 60. So that's a 333. And again, notice that ratio is less than 1, so this is going to be a negative number, as I said. And if you want to put Kelvin again here, you can, maybe should, cross it off, and then become 200 times 4.2 times the natural log of 328 divided by 333. And so negative 12.71 joule Kelvin. And so the total then is what you get when you put the two together. So I'll take that number and add it to that negative number and get a net positive of 1.18. And so here is how we would phrase the change of entropy of the whole universe. Okay, so there's a little entropy calculation example. All right, hope that helps.